So the ANOVA F statistic is a ratio where the numerator is the variability between groups. So that is, if we look at these three sample means, the formula itself involves some sums of squares, but it's a measure of about how far apart these three numbers are, and the denominator is the variability within groups, which is more like an average of these standard deviations. These standard deviations here are the variability of that quantitative variable tip percent within each group. So it's not a straight average of these, but it is related to what these numbers are. And in general, this distribution does rely on these numbers not being too dramatically far apart from each other. But we'll get into that a little bit more after we've established the procedure and we start getting into conditions for inference. As we can see, the F statistic is given to us right here, 20.679. So this is what the output looks like in StatKey. We can take our F statistic, and also we have this button here that if we click on it will give us some more detailed information, but we don't really use the detailed information for this course in the ANOVA table as much as we did for the chi-square table. The distribution we want to use to look at this F statistic is the F distribution, and this is all named after Fisher, a fairly famous statistician who developed a lot of the stuff that we use, where we have 2 degrees of freedom now. Not 2 degrees of freedom, but 2 different numbers that both represent degrees of freedom. One comes from the numerator and one comes from the denominator. The one that goes with the numerator we refer to as the degrees of freedom for groups, and in some books you'll find that referred to as the degrees of freedom for the numerator. Even in this course you'll find occasionally questions in StatKey in Wiley Plus might phrase it both ways, right? So we want to be able to go back and forth between these 2 different ways of asking about degrees of freedom. And we have degrees of freedom for error, which is degrees of freedom from the denominator. This is called error because it is what is introduced by the amount of spread that's in each distribution. Well, that's the error that's making it difficult for us to just compare these means in a straightforward way. So the degrees of freedom for the numerator is k minus 1, where k is the number of groups. So in this case we had 3 groups: good weather message, bad weather message, and no message at all. And therefore our degrees of freedom for groups is 3 minus 1, which is 2. N is the total pooled sample size from all groups. In this case we had 20 in each group and 60 total from the 3 groups. So this is equal to 60. And so our degrees of freedom for error are n minus k, which is 60 minus 3, which is 57. Notice that if you add these together, the 2 and the 57 get you 59. If you add them together, you should get n minus 1, where n is the total pooled sample size. So we have 2 different values for degrees of freedom, and we need to specify both of those in order to get an F distribution curve. This curve here is what we would call F 2, 57. 2 degrees of freedom in the numerator, 57 degrees of freedom in the denominator, and we're going to find our F statistic on here. Our F statistic, remember, was F equals 20.679. We can see this goes out to 20 here. This is about 20 and a half, so probably right about here is where our F statistic is. And therefore our right tail is very tiny, and we would have a p-value very close to 0. So now that we have a p-value, we can go on to our conclusion. This is a multiple comparison test, so we do have a two-part conclusion. At least if we get statistical significance in part 1, then we want to answer in part 2 also, where is that difference observed. For part 1, with our p-value so close to 0, we of course have very strong statistical significance. So for part 1, we're going to say that we have overwhelming evidence of a difference in means in this context. So part 1 of our conclusion is that we have overwhelming evidence that a message about good or bad weather has an effect on tips on average. Note that because this is a randomized experiment, we can phrase this in a causal kind of language. Since it's not a random sample of bills from a lot of restaurants, we really can't necessarily extend this out to a very large population. But we can establish the causality here. So we'll choose language that focuses on establishing that causality. For part 2, we need to look back at those different sample means or look back at that box plot and see where the biggest difference is observed. So we've already noted that the biggest impact seems to be with the good weather message, that seems to improve tips some, and that there's maybe some speculation that the bad weather message also has a negative effect on tips. So part 2 of our conclusion is very similar to what we observed before going into the ANOVA process, just from looking at this side-by-side box plot and seeing whether there appears to be a difference that's worth investigating. In part 2 of our conclusion, we want to repeat those observations. Something that has always occurred to me when I get to the end of this example is that it's not really stated anywhere in this background what the weather was actually going to be the next day. So it would be interesting to see if this still holds up under different weather patterns as well. It's possible that the weather was supposed to be very nice the next day and that the bad weather message was perceived as a strange thing to say for that reason, right? We don't really know these details. So that makes it a little bit difficult to describe how much we might try to extend this result, but we still have certainly established some sort of causal relationship. We just don't know the exact environmental variables that need to be present in order to capture it again.